All right, welcome to a new lesson here. This is 6.2 in McGraw-Hill Ryerson Pre-Calculus 12 textbook here. Is where we're studying in right here. And we're talking about identities, trigonometric identities. That's the title of the section, of the chapter, I should say. And so we're talking specifically today about sum and difference identities. So you'll recall in our previous lessons that we talked about these identities here in 6.1. We talked about reciprocal identities, quotient identities, and Pythagorean identities. We also talked about the fact that identities are true all the time for any value of x that you put into this equality statement, for all values that are permissible. So again, we have to follow mathematical rules. We can't divide by zero, can't take a square root of a negative number, and things like that. So anything that's possible to have an actual value to, identities are true statements for any possible value of x. They're true all the time. So that means we can use them to express maybe one expression, okay, trigonometric expression. We can totally change it to make it look like something else, okay? So for example, sine of x can equal 1 over cosecant of x using one of the identities. So if you see 1 over cosecant x, you know that's exactly equal to sine x for all values of x that are possible, okay? All right, so sum and difference identities here. We can use, okay, sum is adding, difference is subtracting, okay, right? So trigonometric identities can be expressed using related angle measures. Gotta get myself out of the way there. Related angle measures. Okay, what does that mean? Well, obviously 90, for example, can also be equal to 60 plus 30. Okay, so knowing this, how does that relate to trigonometric identities? Okay, so does it hold that the sine of 90 equals the sine of 60 plus the sine of 30, or is it just sine? Oh, my screen's paused. Sorry, guys. For some reason. Here you go. Now you can see that, hopefully. Thank you. I know what that's the chat was for that, wasn't it? So is this true, or is it just true that we have, this going on? Okay, because this is equal to sine of 90 for sure. But what about the individual? Can we, you know what I mean? Like, we can't distribute this like multiplication. So what can we do? So let's check, okay? Let's check with another example. For example, sine of 90. Can we do that in terms of sine of 45 plus sine of 45? Let's check it out. So sine of 90, I know the sine of 90 is 1. Okay, that's 1. According to my unit circle, and I have the first quadrant here, you should have the first quadrant memorized, okay? Unit circle, the angles, and the points. We're going to look at sine of 90 here as being 1. And I'm going to look at sine of 45 as being root 2 over 2. Okay. So is this true? Root 2 over 2. So does 1 equal root 2 over 2 over root 2 over 2? Well, let's see. I have, this is like half of root 2 plus another half of root 2. So that just equals root 2. Obviously, that doesn't work. Okay? That doesn't work. So this is not true up here. So what is true? How can we express sine of 90 in terms of other angles that either add or subtract to 90? And that's what we're going to focus on today. Well, it just so happens that it's not as easy, it's not as straightforward as you might think. And these identities are in your textbook. And if you're following along with our textbook today, it's 300, page 300 exactly. And I do have little clippings here on the video as well, lesson. So sine of a plus b. So again, we took a look at sine of 90. And if you could split up an angle into a sum of two angles, this is how the equality works. So it's a little complicated. But we can easily break this down. It's not a big deal. But the sine of a plus b equals sine of a times cos of b plus cos of a times sine of b. So you're going to want to write these down. I would encourage you to memorize these. There's going to be a bunch of them, so it'll take some time. But for sure, the more you know them, the better you know them, the quicker your homework's going to go, the easier and quicker things will come to your mind, and you'll be able to understand a little more fully too if you have more of this committed to memory. So do your best with that. But for now, we'll check back here. You know, it's okay, no problem. So sine of 45 plus 45, that would be equal to sine of 90. I know that's equal to sine of 90. And that should be equal to 1. So let's test this trigonometric sum identity. This is a sum identity. Let's verify. Sine of 45 is root 2 over 2. Cos of 45 is also root 2 over 2. Unit circle tells us that. Also 45, 45, 90 tells us that. Right? Sine of 45 here, opposite, 1 over root 2, which simplifies to root 2 over 2. Cosine of 45 is adjacent over hypotenuse. That's 1 over root 2, which, as you know, simplifies to root 2 over 2. Plus, now I'm going to multiply this as well. So cos of 45 now, well, root 2 over 2 times root 2 over 2. What do we get? I get root 2 times root 2 is just plain old 2. 2 times 2 is 4. And it's the same thing over here. Now, 2 over 4 we know is 1/2. So if that's 1/2, and this is 1/2, right? I have 1/2 plus 1/2 equals 1. That is true. So this is verified with one example. Let's do another example. And again, we're going to focus on our special angle triangles. Okay? Let me just make a little space here. It's not enough space for me to work. Come on. There you go. All right, so let's work on our special angle triangles, and we have sine of 60 plus 30, which of course is sine of 90, right? Which is 1. We know that. So let's test this. Sine of 60. Okay, so here's 60. Opposite over hypotenuse. That's going to be root 3 over 2. You see that? Times cos of 30. So cos of 30 is adjacent over hypotenuse. Oh, that's actually going to be the same thing, right? Sine of 60 and cos of 30 are the same. Oh, okay. Whoops. 3 over 2. Plus cos of 60. So cos of 60, well, we said, oh, wait a minute. Cos of 60 is 1/2. And sine of 30 is 1/2. Oh. 2. Okay. I'll put brackets around there so we don't get mixed up. All right, so this is what this looks like. So let's see, root 3 over 2 times itself. Well, that's like root 3 squared. That's going to be 3 over 4. Plus 1/2 squared is 1 over 4. And look at that. 3/4 plus 1/4 equals 1/2. That is verified to be true as well. So we've done 2 examples here. They're both true. That's not a proof, but that is a verification that should allow us to understand that, hey, these are probably going to be the identities that they're said to be. So here are some identities for all 3, sine, cos, and tan. Notice that sine and cos are very much the same. Tan's obviously a bit different. Tan's always a bit different, right? It's kind of the black sheep of the trig family, isn't it? Anyways, tan can just do its own thing. Go tan. Go tan. All right. So, again, we could do a cosine example, which I do have one set up here, and these values are just random. They're, they're not on the unit circle. So let's use our calculators to figure out if we could have, if these are making sense. So again, I'm going to use my calculator here, and you can double check on yours as well. But I'm going to do, first of all, I'm going to do cos. Let's turn this on and get out of there. Quit. Clear. Let's do cos of 57. All right, so cos of 57, oops, that's degrees. Let me just check. Radians. Let's go to degrees. Your calculator should be in degrees. Okay. So we're going to try cos of 57 again. I bet you I'm going to get a different answer. Very different. Okay, so cos of 57 degrees is, what was that? 0.5446. 0.5446. Okay, so 57 is made up of 50 plus 7. So that's why I have A is 50, B is 7. So we've got, for cos, it's cos, cos, minus sine, sine. All right, and we flip the angles there. So I've got this set up according to this sum identity, okay? They are a bit different. Sine is going to be sine cos plus cos sine. This one's going to be cos, cos, sine, sine. And sine is going to be opposite here. So again, as you work on that, just remember there are some slight differences. They're very similar, but slightly different. Okay, so cos of 50, let's quickly go through that. So cos of 50 is 0.6427. 6427 times the cos of 7. Cos of 7 is 0.9925. 9925. Okay, so we're gonna multiply those, and we're gonna subtract. So we need to find out the sine of 50 now. Sine of 50 is 0.766 times, I'll just put the secondary brackets there, sine of 7. Sine of 7. Now, what's sine of 0? 1. Sine of 0 is 0. Sine of 90 is 1. So is this going to be close to 1 or close to 0, you think? Close to 0. 0.121. Okay. All right. So yeah, I'll just maybe pause the video here. I'll just evaluate this. You can do that at home as well if you're on your way. Save a little bit of time here. Okay, so now that we have these evaluated, we see that the left side doesn't exactly equal the right side down to, what is this, like a 10,000th or something? Which goes to show that when we use decimals instead of exact values, they're approximate. So if you're going to round these decimals are truncated. That means they've been cut off, like a trunk of a tree. They're shortened. So when you shorten, you miss all those little decimals there. And all those little decimals over time, they add up, and we have a discrepancy. So I would say, though, to test this, though, to be the exact same to 3 decimal places is a pretty good indication that we're on the right track here. Okay? So those are the sum identities, and tan looks a little different. So again, working with tan is a little bit different. Now, I'm just going to show you here what this working out for tan of 31 is. So give me a second. All right, well, you know what I found is I found that I did a test on tan of 57. So we can pick any number, can't we? We can pick any number, 31, 57, whatever. So I chose 57, and I decided to split that up into 25 plus 32. Okay, and then you can see on the left here, I just did this on my calculator, got 1.54 for the actual decimal ratio for that. And then when I plugged in 25 for A and 32 for B in this expression up here, when it's all said and done, I ended up getting the same number. So that's just some verification for these sum identities. Okay. All right. There are also difference identities. Okay. And I put them side by side here because they are very similar. Okay. They're very similar. Notice the sign. Okay, here's the one we just looked at, A plus B, right? So sine of A plus B is sine A cos B plus cos A sine B. So if it's a sum here, it's a sum here for sine. Sine, sum, sum. Think about that. Sine, sum, sum. Okay? Sine minus minus. Sine, sum, sum. Sine minus minus. They're the same. Okay? The sign is the same for sine, for sum, and for difference. Okay? Sine is the same. And it alternates sine cos, cosine, sine cos, cosine. Cosine, all right, cosine is it's cos cos sine sine, and it's opposite signs, always opposite. So this is a minus, this is a plus. Cos cos, sine sine. Just flip the angles. All right. Very similar, and then of course tan here is exact same except it has different signs as well. So if we notice that all of the signs, like the SIG ends, are different than the sum, their sum parts, right? So sine is the same, plus plus. Over here it's the same, minus minus. Here it's plus minus, minus plus, and so on. So you have these for reference. Let's do this one here as a difference, okay? Okay, so I changed my mind here. We're going to do not 105. We're going to do sine of 15, and the reason why is because I can use some common angles, some of my important angles for my special angle triangles, and I can make this into a difference. So let's focus on a difference here. Let's make a difference. Okay? So sine of 15 is a difference of what? Well, that's going to be what two numbers here looks like we have a difference of 15. And actually we could do this as a sum or a difference. Sine of 15 actually, right? So let me show you. What I mean by that is we could do sine of 45. Well, I guess we can't really do it as a sum. We can do two differences. And we're going to pick sine of, let's do 60 minus 45. So we could do 60 minus 45, or what I was thinking was you could do 45 minus 30. Okay, so it would be a difference both ways, but you could do it two different ways. All right, so let's try that. So what is that going to be? Well, where's the difference? Here it is, the very top of the screen. Okay, so the first angle A is going to be 60. So this is going to be sine of 60 times cos of 45 minus, because remember sine is the same sign, cos of 60 now times sine of 45. So if we evaluate this, again, unit circle or our special angle triangles, you have those memorized. Sine of 60 is going to be opposite over hypotenuse, root 3 over 2. Cos of 45 is going to be 1 over root 2 or root 2 over 2, however you want to write that. Either way. Actually, let me just do it the other way just in case you like doing it that way. I don't really care. So 1 over root 2. Let's try that. It's not going to be as nice and handy when we multiply that, but cos of 60, cos is adjacent over hypotenuse, right? So that's going to be 1/2. And sine of 45 is 1 over root 2. Okay. All right, so, first of all, I guess we should evaluate what sine of 15 is. What's sine of 15? Well, if we get on our calculator there, sine of 15 degrees, 15, hello, 0.2588, okay, that's a decimal, 0.2588, and if we get an exact answer over here, we can check that exact answer by dividing on our calculator and see if the decimals line up. So let's see what we have. So if I multiply this now, this isn't going to be as pretty as we had before, but this is going to be root 3 over 2 root 2, okay, minus 1 over 2 root 2. You guys see that? We multiply top times top, bottom times bottom. So this is going to be root 3 minus 1 over 2 root 2. Okay. Now, let's just, for comparison's sake, let's see what the decimals look like if we were to actually write this as a decimal. So square root of 3 minus 1 is this, divided by 2 root 2. Oh, look at that. 0.2558190,451. They're exactly the same. See, sine of 15 up there, and this value that we've got here. So they're the same. Okay, 0.2588. So, yeah, some difference, either known angles. If you're looking for an exact answer, try and make the sum or difference of two angles that you have on the unit circle or in your special angle triangles. Then you'll be able to have an exact answer. Okay. So that's sort of part one of this lesson, okay? We're going to get through part two as well, which is similar but different, okay? Similar but different. Now, if we have sine of a plus b, but let's just say that we have sine of a plus a, okay? Sine of a plus a. Well, that's the same as sine of 2a, okay? So if the angles are the same, we could probably come up with a new pattern, and we could write a new identity for a double angle identity. And that's what these are, double angle identities, okay? And they're basically saying if you have sine of some angle, you can express that trig value a different way using angles that are half the size. So this is important to note, okay? if we have sine of 2a, I can write this in terms of sine of in terms of 1a. Okay? And look over here in this chart. So if 2a was 80, then a is 40. Okay? If 2a is 100, a is 50. You get that, right? Or half. Now, what does this mean for us? Well, sine of 60, guys, sine of 60, if that's 2a, I can rewrite that in terms of the angle 30, which is half. And again, it all comes back from these patterns. Look at this, sine of a plus a, right? Sine a cos b, which would be sine of x times cos of x plus cos of x times sine of x. Well, that's just sine a cos a plus sine a cos a, or 2 sine a cos a. So we've got new patterns emerging from the fact that what happens if the angles are the same. Okay? So sine of 60 can be written in terms of sine and cos of 30, just like this. So sine of 60 we said was that root 3 over 2? Root 3 over 2. Sine of 30, oh, here we are. Sine of 30 is 1 over 2. And cos of 30 is root 3 over 2. Well, this is just 1 times root 3 over 2. So we have root 3 over 2 equals root 3 over 2. Verified. Okay. Other ones. Cos of 2a can be rewritten as cos squared a minus sine squared a. So if I have cos of 120, I can actually rewrite that as cos squared 60 minus cos squared 60. This one is this angle is not on the unit. Is it on the unit circle? 120? No, 135. No, it's not on the unit circle, but 60 is, right? So if you want an exact answer of this, treat it as a double angle, and then use cos of 60 and sine of 60. Okay. All right. So I'm not going to do too much more with those double angles, just because the lesson is lingering on here. So I'm going to run through just some examples from the homework here, just to kind of get you going a little bit. But I do have on this screen right here, I have the identities that we studied in 6.1 and the new identities here for today. So I'm going to zoom in on this, the key ideas for today. Okay, and this is our lesson. This is our lesson. You can use the sum and difference identities to simplify expressions to determine exact trig values. So if you have, for example, sine of 105, which is not on the unit circle, but you know sine of 45, and you know sine of 60, and you know cos of 45, and you know cos of 60, you can find an exact value for that using these sum identities. And of course, the difference identities are very similar. And double identities. Now, here's more double identities than what we had just talked about. Sine of 2a, okay, there's one double identity for sine, but there's 3 for cos of 2a. We looked at this one, the first one, but because of other identities, you can rearrange this, or you can transform this into looking 3 different ways. So cos of 2a, you can use any one of these to rewrite cos of 2a. And here's tan of a over there. Okay? All right, I'm going to make another video of homework for 6.2, so I'm going to end this video here now. That's your lesson for 6.2. And yeah, sum and difference identities and double angle identities are what we studied here today in this lesson. Sum and difference, part 1, and then the double angle identities, part 2.